First of all, come to my presentation, and I'd like to thank the conference organisers for allowing us to present our paper here. We are, so we've been thinking about this for a long time. We have seen through the Creative Destruction Lab now hundreds of machine learning, AI and related startups coming through, and it of course caused us to wonder how to think about the economics of all this. And whereas the papers this morning started at the aggregate, then to the market, we started at a different place, and that is the individual. Some of you may have seen a little bit of this presentation at the NBER a couple of months ago, but it's changes towards the end, so stay tuned. So as we've heard already, quite a lot, recent artificial intelligence, all the recent deep learning neural networks and so on, it's all about prediction. That is what AI has achieved. It allows you to take, for instance, a picture and be determined, have the computer describe what is in that picture. For instance, one of the most popular apps allows you to take a picture and it will tell you whether it is a hot dog or not a hot dog. And you might think that's useless, but what's going to happen if you actually go down to one of the vendors there on Bloor Street, buy a hot dog, take the picture and it says it's not a hot dog, then we'll see whether you trust the machines or not. Okay. But actually, it's more significant than that. I don't know how this video is going to come up here, but this is going to be a video I'm going to show you of a Tesla, which had a dash cam, and you'll see what happens. If we're a bit lucky, we'll get to hear the alert beep that happens there, but let's have a look. So they're just traveling down a road. Now, what you didn't get to see, there was an accident there. And that accident was caused by this car, who's, I guess, going to pay for it. But this was the car immediately in front of the car in question, the Tesla. And it obviously didn't come off unscathed either, and in fact, collided here. But look how far back the Tesla actually managed to stop. And there was a notification that turned up well before there was any hint of an accident, that this accident was going to occur. And the Tesla, despite having what is well known to be like way substandard abilities to sense the world around us and all that, things like that, had this enormous predictive capability. And you can imagine how that would play out. So that's the significance, and it's all about prediction. Now, what we're going to do is we're not going to hold back, as some of the other papers is. We're going to dial the prediction machine up to number 11 here, and see if we can think about the consequences that means for AI, for when prediction machines will be valuable, and the human roles as part of that. Okay, so how do we think about prediction as economists? Well, normally what we do is we have individual agents who are assumed to act according to decision specifications such as this, where they maximize some action to maximize a utility function that is a function of that action, and also some state of nature. And then they couple that, when there's uncertainty, with a prediction, S, which is a signal of that state of nature. So we have here these sort of two components. We have here the prediction entering into people's utility, into the people's decision problem, and then they choose accordingly. And we also have this, which is a function that describes how states and actions map into rewards. Okay? The root of all worry about AI is about stuffing up, giving an AI a utility function, and they go crazy. The problem we have with the Terminator is they had a utility function that wanted to kill people. If you watch Terminator 2, when that got reprogrammed, it was much better. He'll live. So that's the root of all worry. But where does that come from? Okay, so basically, and it could be different, obviously, for how versus, this was another one of things. You can't read it here, so you seem to be using email that leaves in trace of your collusion with Russia. Would you like me to stop, or would you continue doing it? Anyway, so this is when AI lets us down or can be assistance. So where does this come from? Okay, so when you're starting to think about how can AI actually improve and improve decision making, you have to actually start to think about models where decision making isn't perfect. This was something obvious to Herbert Simon, but we often neglect this. Where does this utility function actually come from? Okay, one is we get a utility function by thinking through things. We sit down and we think about, well, in this scenario, and what is the value of this particular action and what are the trade-offs, and we actually go through introspection thinking about that. Okay? Another place this comes from is experience. We have learned by running the car into the wall enough times, or whatever it's going to be the equivalent that we would have, is we learn that there's certain values to this in terms of how we feel, what we like, what are our tastes. And then sometimes, as Becker and Stigler would say, is like it comes at some fundamental level from everything, and it's just how we think about the structure of information that changes that. That's fine too. But we're going to call the process by which we may actually arrive at a utility function, and we're going to give it a name, judgment. Okay? And that's the process of determining the value of actions in a given state. So in other words, a decision is made up of a prediction, and it's made up of an application of judgment. And obviously, to make things interesting, as you'll see in a bit, we're going to assume that that application of judgment doesn't come for free. There's some actual economics that is got to be behind it. Okay, so the model we use is a model by Bolton and Farah-Grimaud from 2009, which actually had a similar setup to, this was pre-AI. They had nothing, they weren't thinking about that. They were thinking about some planning problems. And the timeline is this, or the way the model's set up is this. Is you have an action that you can take, and there might be a safe action, and then there's a risky action. The safe action, the risky action is obviously the payoff's going to be dependent on the resolution of a state. And that state could be either state 1 or state 2. Okay. So the safe action has a payoff of S. The risky action has a payoff of either R or little r, where big R is greater than little r, in either of these two states. It could have either of those things going on. So you know it's going to be state contingent, what occurs, but you don't know what the payoff would be. And we're going to assume that the safe action is the default. In other words, we're going to assume that the safe action is in between two, so there's no obviously dominant action. Okay? And the probabilities of state 1 are going to be mu and 1 minus mu, and we'll make state 1 slightly more likely. The interesting part of this model is there's also a priori, prior to the application of judgment, you do not know whether R or R is going to be the outcome, the reward in that particular eventuality, when the risky action is chosen and it's state 1. But you have priors of V and 1 minus V on that, and same for the other state as well. So the first question we want to ask ourselves is, are prediction and judgment complements and substitutes in this environment? In other words, if I had a prediction, or if I had a better prediction engine, would I end up expending more costs to work out what the payoffs are in these risky states? Because I can go and do none of that. I can just go and just take the safe action all the time and not know any of these things. So the simple intuition is, if you don't know the payoff, then knowing the state is not valuable. You know, the payoff, it's all uncertain what goes on in the risky action, you may as well just take the safe action. And the alternative is, if you don't know the state, then knowing the payoff is not valuable. Why work out what the risky action is if you don't know, what the payoffs in the risky action are, if you don't actually have any way of working out which state is going to occur, what the level of risk is. So this suggestive complements, and Scott, in a discussion of this, a similar line of research at the AEAs, had suggested that. But actually what we're going to show you here is a bit of economics says it's not quite true. It's not quite true. So what happens if you have both prediction and judgment? If you have both prediction and judgment, let's imagine you've got prediction where you can, before taking the action, you know now exactly which state is going to occur. Okay? And so, and moreover, you have worked out what is happening in each state. Then basically with that, you can get a first best outcome that you are, depending on what the resolution is, if it's little, if the high outcome in the risky state occurs, then you'll choose the risky action. Otherwise, if you've learnt that it's not, you choose the safe action. And similarly, down here as well. So if you have both prediction and judgment, you can do something great. You can make fully optimal state contingent actions. You've got both of these things at your disposal. Okay? Now, everything interesting happens when we don't have that. Okay? So what if you just have prediction, but you don't know what judgment is? Well, if you just have prediction, so the value of prediction in the absolute it allows this state contingent decision making, and you can optimize. But if you just have prediction, what you can do is you either take the risky action or the safe action depending on what your guess of your utility function is. Okay. And then what is the value of judgment, though, in the absence of prediction? This is what I want to talk about most of all. What's interesting here is there is a value to judgment even if you don't have any prediction at all of what's going to go in the state. And the reason is this, because as you say through introspection or something similar to that, go through, well, if that state occurs and I take this action, what do I think the payoff's going to be? You could find that in fact the payoff is the same in both states, regardless of which ones occur. In other words, you could find out that in fact there are, there's with some probability that you'll have a dominant action. That you'll have a dominant, either the safe action will be dominant or the risky action will be dominant, depending on that process of judgment alone. Now, in order to do that, you've got to go through the exercise of thinking through what you do in each of these states to work that all out. But if you do that, there may be a value, and it may resolve your conundrums and things, and give you essentially no value to prediction at all. Okay, so that's where the economics comes from. The model we have, which I'll whiz through very quickly, is to work out the payoffs you need to think. And thinking basically involves you sitting down there and saying, I wonder in state I, what's my payoff going to be? I could apply judgment or I could just choose. If I apply judgment, I learn with a probability lambda and I don't learn otherwise. And then I can do that to the other state. And I can face the same sort of cost function. What that means is that if I choose to think about what my payoffs are, it's going to take me more time. Okay, it's going to take me some time, but if we can, with this model, we can work out exactly how long that's going to be. Okay, and then of course, once you've done full judgment, you choose anyway. Okay, so basically what this means is any payoff will be discounted by the potential application of judgment. So your options are, you could learn neither, you could learn both states, you could learn one state, you could learn one state if the other turns out to be good news, that is the risky action is great, learn the other one state, and then the other only if it turns out to be bad news. And with a couple of assumptions that I won't go into, it turns out that not all of these options are worthwhile doing, and you can calculate that some are dominated. Two ones of particular interest are learning one state, just thinking, what will I do in state one? Sometimes that's enough for you. And sometimes learning one state and then going on to learn some more if it turns out that that's supported the risky action. Those turn out to be two things that you might choose to do, and they depend on various thresholds in terms of the cost of judgment. The higher the cost of judgment, the more judgment you end up doing. In other words, you'd, in the absence of prediction, learn more than one state. So we've only got two states here. You can either do no judgment, you can do it on one state, or you can end up doing it on two, and the more you do that. Now, that is where the substitutability comes in. Because basically, as you learn more about those states, it is true about what you want to do, the value of prediction goes up. However, once you've got to start going through the whole problem, you've now got a chance that you'll find out that you don't need prediction at all. And so the value of prediction, incremental value of prediction, actually starts to decline. So we have, I can show that in mathematics if I want. The interesting thing about the complements and substitute, it is contingent on one of the variables that we're expressing a complement over, which is the cost of judgment. So it's not perfectly satisfying in that regard. And we can do other things. We can look at prediction tools, one where there's some probability that the AI you have generates a prediction at all versus not, and also there might be some probability that it is reliable, that it's actually correct or not. And we can look at your preferences for whether you'd rather have an AI that told you, gave you a prediction more often versus one that was somewhat reliable. And it turns out that what happens to design as judgment becomes easier is that as judgment becomes easier, you care more about getting a higher, more reliable prediction than you do about a prediction at all, which is consistent with what I just said before. Okay. In the final couple of minutes that I've got, where can all this be applied? This is a simplistic representation of the problem, but it would be interesting to think about complexity. If there's one thing that's cropped up in the are humans going to survive all this mess stuff, it's an assumption, and it is an assumption, that humans are able to handle more complex things than machines. And when we invent new stuff, they happen to be more complex, so there's hope. That's the Acemoglu-Restropo argument. So we can put complexity in here as well, and think about that in terms of an n-state model rather than just a two-state model. And so an n-state model, you can imagine that if you can come up with a prediction of which of those n states is going to occur, that's very valuable AI. But actually, what's more likely is that the AI will be able to do a very good prediction on some states, but the rest will be, well, they'll know if it's going to be a block. So in other words, something akin to a partition occurs. Okay, so part of it will be predicted by AI, and if these things are complements, you'll apply judgment to it. And then the rest, well, since you haven't got a prediction, you'll just take the safe action. The ordinary thing. You don't have to do one of these complicated state contingent actions, or you're not aspiring to do so. So as n increases here, the value of prediction and judgment are actually going to be reduced. Because we get complexity, but unless we change the margin of things that we actually can discern, it's not going to change very much. Similarly, we can apply this to automation as well. The way we consider automation is not too dissimilar from Vasily Leontiev, who worried a lot about technological unemployment. He was the first person who was really, he saw the horses go and he says, that could be us in his lifetime. So any worker who now performs his task by following specific instructions can in principle be replaced by a machine. Notice the specific instructions bit. That's what's interesting here. If you're going to have a prediction and then a machine do something, you have to tell the machine what you want it to do. That means someone already has to had gone through the judgment and know the utility function, okay? And that could be a costly endeavor in of itself, obviously. So what are we going to see here? We're going to see some tasks that can be predicted. People, through experience, knowledge, and other things, engineer ourselves a machine. And so we'll get a machine, but we'll get a different sort of machine than the machines over here that don't know better than to do the one thing. These machines, powered by AI, will be able to make a state contingent decision, just like the Tesla car we saw. Okay, that was a state. We always had the ability to have machines to go stop and go. The problem is they didn't know when to do so. They had to be put on tracks. The difference now is we graft a prediction engine onto them, and we know what they want to do. And we all know that driving was always easy. If you've had to teach a teenager to drive, think about it a second. The reason you are screaming is not because they don't know how to use the car, because they don't understand what the road is telling them in front of them. That's why you scream. They're screaming actually because of the prediction, not necessarily because of the judgment or how to operate a car. In the middle here, we're going to have things that we still need humans to do, because we haven't worked out how to code them into a machine. And so that's going to give us different parameters here as we crank up that prediction engine number 11. It's going to affect both this and this. So it's a bit ambiguous what's going to occur there. And then finally, we can actually apply this to something a bit more economic that hasn't been thought about, which is contractability. The akin to automation, being able to tell machines what to do, is also our ability to write contracts that tell parties or people what to do. Okay? And we need, one of the reasons things might be non-contractable is we often don't know what to do. Herbert Simon saw this. He said the difference between an employment contract and a physical contract was we don't know what to tell, in his day, the secretary, and it was a her definitely, what to do. Okay? But this happens in our contracts as well. That is what's non-contractable. So again, this will be interesting because we can take that and we will think if we just, and we did this in the paper, grafted on the model by Steve Tadelis, and think about how outsourcing and integration might change as we get different prediction. Not just in capital, which could be more flexible and hence more capable of outsourcing, but also in labor, which is going to be valuable in precisely non-contractable elements, and so you want to bring the outsourced workers that the New York Times was complaining about back into the firm. So I think these things are interesting ways to go.
It's very interesting, and I found this paper very interesting, and it relates to a lot of stuff that we've discussed this morning. So the question is, what is the stuff that AI can do and the stuff that AI cannot do? And I have to say, I mean, Matt Taddy has left, but my interpretation of AI was much less broad than his, and I'm thinking more about the tools rather than the whole thing. So, what do I have here? So what this paper does, it gives a name to the stuff that AI cannot do, and it calls it judgment. And I find this concept extremely useful. And then the main result, there's a lot of fancy theory stuff, but the main result is actually, the way I read it, is that judgment and prediction are complements. So this, at lunch, for instance, we saw this great progress in diagnostics. And the implication we had is this will put doctors out of business. This type of result says the opposite. This type of result says that as diagnostics tools get better and better, the judgment of doctors will become more and more important. So I think this is a very practically an extremely important area to explore. What the paper does pretty well is to explore the relative demand for these two things, AI prediction and human judgment, under various circumstances. There's two things I like a lot about this paper, besides the result. One is that it builds on this very unknown paper by Bolton and Forgrimo that tries to theorize thinking. It's a great paper that has a total of 19 Google citations, and I'm very happy to see it used. I think it was before its time. And I think this is the beginning of a very important research program for economists, which is to try and understand how AI relates to concepts we're familiar with. And this is, I think, the first theory paper that does this. So what I'm going to do is I'm going to present a super simple, ridiculously simple example of a situation where this matters. And I'm going to use it to make 4 comments about suggestions about the paper. It's more than the suggestions about the paper are suggestions about this research program, stuff that we may be interested in looking at. So the example is, it relates to our profession, and it's college admissions. And I'm sure each of you, if you teach in a university, have had a colleague come up to you and say, we should let AI do college admissions because they're much better than us. So I wanna take that seriously. And how would we do it? Well, we have a ton of information that comes into applications. And then we have very precise performance measurements. We have grades, right? The grades are super precise. There's an econometric problem about sensor data because we only observed it about successful applicants, but I'm sure you can find ways to experiment a little bit at the margin, stuff like that. So it sounds like an amazing idea, right? So let's think about it through the lens of this paper. So what we do is we have data. Data comes in now. It's application. 1 year from now, these people will take, I'm thinking about MBA students, so they will take their core exams. This is a very precise measure of how they're doing. And we put the two things together. I'm sure we would have an amazing predictor of performance. The question, obviously, is that what we want? Is that what we're trying to maximize as a college, as a business school? And the answer is clearly no. Our goal is, when we admit people, is not to maximize their grades in the core course, but is to create successful, influential, ethical, inspiring business leaders who may also make donations in the future, perhaps. And so that part there is judgment. That part there is judgment. You have to kind of think through. You can use evidence, you can use data, you can use, but you won't have that type of machine learning that's going to help you. So I'm using this because here comes the first suggestion. The first suggestion is that, and it's probably in your mind right now, you're using the wrong state. You're using the wrong state. So the problem is here is that the state is different from the payoff. So you should be trying to predict something that's closer to the payoff. So for instance, one thing you can do is, instead of predicting the grades in the core courses, you could try and predict the quality of the first job. This starts being a bit more sensible, right? But what happens now? What happens now is that this is something much messier, because it's AI is good when you have a very nice y variable. And here you have something that instead starts to be very multidimensional. So you can do it, but you face a trade-off. When you do this, you get something, you reduce the importance of judgment, so you improve judgment in a sense, and you worsen prediction. You can go even further. You can try and predict the payoff directly. That sounds extremely hard, right? Because it also starts contradicting the assumption of stability, because the relationship between applications and this type of long-term outcomes is probably unstable over time. And so you're probably going to have, even if you could wait all this time, you would probably have bad predictions. So what's my suggestion here? My main suggestion is that what we should think about it is endogenizing the state variable. So try to endogenize what should the prediction target be. And Susan mentioned that, if you let computer scientists do this, they're going to choose the variable. They're going to look under the lamppost. They're going to choose the variable that's easier to predict. Our contribution, I think, is to try and figure out this trade-off and try and figure out which variable is the best solution to these two negative things we're trying to minimize. So my suggestion here is to try and model this type of trade-off and try and find testable ways of seeing if we're choosing the right state to try and predict. The second one is something that I will probably skip because you haven't discussed it. It's very interesting. You discussed the difference between accuracy and reliability. We can take it offline. My general sense is that this is not a very general difference. So you might want to do something a bit more general than put some kind of cost that's entropy-based. Then you discuss complexity. And complexity, I find this perhaps the weakest part of the paper. Complexity is simply defined as the number of states, and only m states can be predicted. And so if you increase the number of states while m stays constant, you get that the prediction technology gets worse almost automatically. So I didn't get a lot out of this. In a sense, it would be great to relate it to more standard computer science notions of complexity, and in particular, the idea of the set of possible hypotheses. So every time you do predictions, you're considering a set of hypotheses. And obviously, the narrower the set of hypotheses, the better your prediction between this set. And you have a trade-off, a well-known trade-off between in-set predictability and outside the set predictability. And so it would be nice if your paper started talking to this. So my suggestion here is to try to think about this and try to think about how judgment helps us choose what the relevant set of hypotheses is. Finally, my last point. My last point is, and I believe this is where we as economists can add the bigger value to this, is the idea that in many of these problems, the distribution over state outcomes is endogenous. So it's trivial, right? You have a credit, you have a artificial intelligence that chooses who gets credit and who does not. You are definitely going to have that people are going to change the way they apply. They're going to make changes to the application, and they're going to make material changes in order to maximize the probability that they get a loan. College admissions is another example. There's a whole industry around college admissions that is exactly trying to game the current system. If we automatize this system, we should definitely take that into account. We should definitely think how this endogenous response will come about. As a number of people point out, AI abstracts from that. This is not their core business. It is instead our core business as economists, and it's need for two things. The first one is theory. We need a theory of how people will respond to any system. And Manuel before made the example of policy making. If we think of more important problems like policy making, that's essential, and it can only come from theory. And the second one is, of course, field experiments, not so much as A/B testing, but large field experiments that have the objective to try and tell us what is the underlying model so that we can make policy over this. So my suggestion is to try and endogenize all this. I think this is part of the research program, not for this paper in particular. Thank you very much.
Okay. Questions? Jim.
So I'm going to, just a comment, you saw framed automation as being one application. And so one of the interesting things historically is that various tasks or components have tended to be some will be automated early, others will be automated later. It's not economical. It's too costly to automate things at one stage. There's a dynamic effect where you automate something, it increases the demand for the product, which changes the economics and the payoffs to automate, making it feasible to automate something else. So you see these long dynamic chains. May be applicable, sort of a dynamic interaction of that sort may be applicable in this context.
Ben?
This is very much a question. I think it's about a key point of uncertainty that has been in our conversations this morning and certainly at lunch, which is, what is the human trait that AI cannot replace, or set of human traits? Is that an empty set or is it a large set? And it seems to me that sort of underlies almost everything we're talking about in terms of our speculations. I think it's very interesting, Joshua, this distinction between judgment and prediction. And I'd love to hear your further comments or others on why we think judgment in some sense is beyond. Certainly that's not prediction per se, but is that, why is that beyond a machine intelligence?
So this issue of judgment, we didn't want to think of it at all as just a sort of residual. While it's very easy to get into what are humans going to be good at, the personal, emotional, and other things like that. We don't have any science on that either, really, except we're guessing that that's the case. But this idea of describing what the payoffs are, with the current technology of AI, if it's all about prediction, somebody has to come in, I don't care how accurate your prediction is, and say what the trade-offs are going to be. And actually, I like that Andrea used the example of MBA admissions. We've thought about exactly that same example. It's, I guess, hard not to, and to think about that. And somebody at some point has to be able to sit down and say, well, what do we care about here? And so even if you wanted to move the prediction line, basically using surrogates, Susan gave me that word, that's the word in AR, using surrogates, is in order to choose that, that is going to require judgment in of itself. So there's a sense in which there literally is no ability for current AI processes to do things without judgment. Now, usually at this point, I get the objection, someone raises their hand, and they may do so if they wish to. I know what they're going to say is, Eric. Eric is going to say, but what about reinforcement learning? There the AIs seem able, they're trying to mimic, for instance, play a game or whatever, or some of these ones might even mimic what a human could do, okay? And so that is true, but even in reinforcement learning, somebody has to tell the AI, whatever we want to call it, what to do. Someone actually has to say, maximize this score in breakout. Someone has to say, the human is the pinnacle of driving expertise, you should follow that, and give them that expertise, which is exactly how we get humans, I guess in the driving analogy, that would be quite happy to end up running over people they don't like, or something like that. The biases come in. But ultimately, at some point, there's this function for people, and there's, I guess, more of a premium placed on it to really work out what we want. When we don't have a prediction, we do all sorts of actions that obviate the need to work out what to do. But once we have a prediction, then we have to think through that. So I think, in response to Ben, I think that's a very big issue.
Great. So Eric, then Jan.
Right. So I'll be quick because I want to get to Jan's question, but your prediction engine didn't work. I wasn't going to say reinforcement learning, but I had a different point. I had two quick points. The first one is I've been playing this game for a long time. What humans can or cannot do with Andy and lots of other people. And one thing I took away was never say never, because with a little bit of it may get a little semantic. Let's take knowing your own utility. It seems like it's hard that seems like the one thing a person should be able to do. Wrong. There are recommendation engines. There are Netflix contests that predict better than I do what I'm going to like, and are better able to say what will maximize utility, what X given what state is actually going to be better for me. So I don't think that it's not, and that's not science fiction. That's something that's been tested right now. That they've done contests. You pick a movie, Netflix picks a movie for you. Afterwards, you watch each of them or a set of people. On average, they know better than you do what your utility is going to be maximized. Now, the second point I want to make, though, is that I don't even think this is the right question. What could humans never do? I'm with Vinod and a lot of other people. It's a set of atoms. At some point, there's no metaphysical reason that a machine can't do just anything. The more interesting question is, what is the time and what can we do now? What are the types of tasks that are going to be easier or harder? And for that, I think that this is a useful framework. So it's not so much never, it's a matter of what are we going to be doing in the next 5 years, 10 years, 15 years, 20 years. There's enormous disruption. I totally think that there's most tasks, there's a huge scope of tasks that only humans can do during that time period. There's no shortage of things that only humans can do. And segregating them that way, I think, is a better way of framing the question.
Yeah.
Right. So if you want to build an autonomous AI system, there's probably going to be at least 3 components. One is a predictor. Call it a model of the world, something that predicts what the world is going to do, or either because the world is being the world, or as a consequence of the actions of the agent. A second component is an objective function, and that's where what we want the machines to do is defined. And the third component is one that tries to figure out a good sequence of actions that will optimize the objective function given the predictions that are produced. And the problem is that the predictions can't be completely certain. The problem about predicting the future is that you're never sure that your predictions are correct. So you have to deal with that uncertainty this model of the world has uncertainties about it, and the, whether you trade safety, you can maximize the expected value of the objective function, the expected long-term value of the objective function. But what about minimizing risk, right? You might also want to kind of minimize the variance of it. So all those are kind of trade-offs that have to be built into this objective function and kind of change the risk factor depending on the conditions. Now, it's actually kind of a problem that people are discussing a little bit in the abstract nowadays in AI systems, because no AI system is actually built this way. Most of them today are basically just supervised learning, and they just have the predictor. Not really the system that actually makes decision is very simple usually. But people are asking themselves the question: if we want robots to run around and we want them to kind of be nice to us, how do we hardwire this objective function to prevent them from doing bad things? And it's quite possible that the answer is that it's too difficult of a problem to actually hardwire the objective function. We're going to have to train it as well. And so there's going to be learning not just in the predictor, but also in the training the objective function. That's what we do with kids, right? I mean, we more or less tell them to, behave in society and kind of tell good from evil and stuff like that. So so that's kind of the next step in AI. We have no idea how to build any of this, right? I mean, the main obstacle actually is kind of, how to get machines to learn this world model. We have no idea how to do this. At least no idea that works at the moment. This may take a very long time. To elaborate on another question, which is what is it that humans will do better than the machines in the long run? There's no, for anything that we can think of, there is no limits in principle to what machines can do. But there's one thing that's properly human, and it's the communication of human emotion, or human state of mind, right? That's human communication. We can communicate with a machine. We could probably get a machine to compose music as well as Mozart, but can we get a machine to communicate its state of mind that we would be interested in, as we do when we go to, I don't know, a jazz performance, for example? So I think the future is bright for jazz musicians. A kind of authentic human experience, I think, will still be something that we give value to.
It doesn't have a mind, it fakes one.
No, it might have a mind.
Know its state of mind. How can you know your state of mind if you have no mind?
It can very well have a mind.